we've achieved something great. We've built the hash table, but it turns out there's an Achilles heel lurking. So let's reflect on what we've achieved so far. And I'll note that compared to a data indexed array, our separate chaining hash table idea uses way less memory, and it can now handle arbitrary data as long as we have a hash code function. That's great. But the bad news is that compared to our data indexed array, where the runtime was just theta 1 because we only had to check a true false value, now it's theta q, where q is the length of the longest list. And now that we've restricted our number of buckets to some number, that means those lists might get long. So a question for you to think about just how much of a problem this is. Let's say we have a hash table with 5 buckets. I want you to give me the order of growth of q, where q is the length of the longest list, and give me that with respect to n. So try that out. Kind of a hard problem, actually. This is an easy, intuitive answer, but getting it right in a fully technically correct way is a little tricky. Anyway, give it a shot. Okay, so it turns out that the length of the longest list, here we're not looking at runtimes, we're just saying how big is q. In the best case, the length of the longest list is n over 5. That's where all the items are exactly evenly distributed. And in the worst case, the longest list has every item, n. So in both cases, whether it's n over 5 or n, we could say that the length of the longest list grows with the number of items linearly. It's theta n. Okay? Now that's super bad, because that means that if we only have 5 buckets, that over time, our contains and our add operations will eventually get slow. So if we have a billion items, that means we're going to have to iterate, if we have 5 buckets, over 200 million every time we call contains and add in the best case, which is not very good. So we want to try and do better. Okay? So let's focus for now on the case where items are spread out perfectly evenly. That is, all of our lists are of length n over m, and they're all equally long. They're q. They're all the longest list. They're all n over m. So for m equals 5, as we just saw, that means that q is going to grow linearly, which gives us linear time operations, which is very bad. So the hard question I have for you is, how do we improve our design to guarantee that n over m is theta 1? So I want you to tweak things so that n over m does not grow linearly. I want it to be constant. Okay, and I'm giving kind of a summary of our setup here. All right, so it turns out what we want to do is not have a fixed number of buckets. We need to increase our number of buckets over time. So if we switch from a fixed number of buckets m to an increasing number, then we can hopefully fix things. We will be able to improve n over m, basically. So if we can keep these growing at the same rate, then we can keep the ratio constant. Okay? So an example strategy we might do is that let's keep track of n over m. And if it's ever bigger than 1.5, then we'll double m. And we call this process resizing. It's just like when we had resizing arrays before. I should mention that n over m is often called the load factor, and it basically represents how full our hash table is. So if it gets too full, add more buckets. Okay? So let's see an example. When n over m is greater than 1.5, we're going to double m. That's going to be our rule. And when we start off, n is 0, m is 4, and our load factor is 0. So let's say we add this apple, and its hash code is 7. And how did that happen? I don't know. Someone wrote a hash function that took this image, and it produces 7. Okay? Now our load factor is a quarter. We add in an x. It has hash code 16. 16 mod 4 is 0. All right, next comes this egg. Egg has hash code 3. Mod 4 is 3. We add a bucket, which has hash code 11, a bow, which has hash code 20, and then we have a helmet, which is hash code 13. So at this point, we have 6 items and 4 buckets, and we are exceeding the rule I just made up, where I said we've exceeded 1.5, and we now went to double m. So what I'd like you to do now is try and draw the results after we double m. So you're going to take all these items and figure out where they should go if we have 8 items. And now one question I have if you don't want to do the whole drawing, is just figure out where the bucket will go after resizing. Okay, so it turns out that the correct answer is shown here, this drawing. And basically all I've done is for each hash code, I'm now modding by 8 instead of 4. So for example, the bucket has hash code 11. So it's going to go in position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That is 11 divided by 8. If you take the remainder, we're left over with 3. So we end up here. Here's bucket. Now the order of egg and bucket don't matter. You could have them in the reverse order, and I would also consider that correct. But all of these other items should be exactly where I'm showing them. Now having resized, the load factor is now only 0.75, which is less than our maximum amount. Now I want to observe a couple things here, which is that whenever we resize, items got moved all around, and in general our lists got shorter. Now here, egg and bucket, they ended up together, but before axe and bow were together, and now they're split apart. It is also possible that items that used to be separate from each other end up getting put in the same bucket. It's all just kind of depends on how the hash codes and the length of the number of buckets line up. Okay. So to summarize here, what we've just changed is we've said that if we allow the number of buckets to increase, then as long as we ensure that the number of buckets grows linearly, then n over m is going to be constant. Okay. So for example, over here I have n equals 19, m equals 5, and the load factor is 3.8, just to remind you what those n and m are. And so basically, if we just grow our m at some rate so that it's keeping up with n, then we can get constant runtime overall. Okay. Now again, assuming that the items are roughly evenly distributed, then we have that the list will all be around n over m items long, and that means we'll get theta n over m runtimes for my operations. And so this idea of doubling when the load factor gets too big will ensure that n over m is bounded above by a constant. That is, it is constant. Okay? And therefore, the worst case runtime for all operations, if we're doing this doubling approach and items are evenly distributed, will be constant time. Now the one issue we have to keep in mind, of course, is that some operations will trigger a resize. They will actually cause the array, a new entire array of buckets to get built and all these items to get moved over. And so let's talk about resize runtime. Okay. So resizing will take theta n time because every single item needs to be redistributed into my new set of buckets. Okay. Now most add operations are going to be theta 1, but some of them, the ones that involve resizing, will be theta n time. Now similar to what we saw with our array lists, as long as we resize by a multiplicative factor, then the average runtime overall will still be constant. And we haven't done this analysis in detail yet, but it's the same basic idea we had with array lists. So now that we have this idea of doubling when we exceed some arbitrary constant threshold, we have a really good hash table. And one other thing I should mention before I move on is that this specific constant doesn't matter. I could pick 3, I could pick 9, I could pick 2, I could pick 0.1. All of those would work fine. And likewise here, I can pick any multiplicative factor that's greater than 1, and it will still get constant time overall. Okay, just a tiny bit more, and then we'll be done with this video. So to summarize our runtimes here, our hash tables that we've built, they, as long as we're doing resizing, will have runtime for contains and add that are constant time. Now I've added a little caveat here that we're assuming that our items are evenly spaced. Because if they all end up in the same bucket because maybe our hash code is bad, then all bets are off. And then I've also added a star here that our add operations are only constant time on average because some of them will cause a resize. So hash code or hash tables are, they have caveats. Whereas a bushy binary search tree is guaranteed to have theta log n, here we have a little bit more to think about, but the runtimes are still quite good. Okay. So to conclude this little video about performance, an even distribution of items, or somewhat even, is critical to get hash table performance that is good. So both tables I show here, they both have a load factor of n over m equal to 1. However, this left hash table is much worse. If we tried to call contains for the value x, it's going to be theta n, because we'll compute the hash table, the hash code, and then step through each item until we get to the end, and there it is at the end. So if our buckets are represented as linked lists, our contains operation will be theta n. So we'll need to discuss how to make sure our items are evenly distributed, and before we can do that, we need to talk just a little bit about hash tables work in practice in Java.